Alrighty, welcome back. Now, drag forces. So, just before I was talking about your stock standard projectile without any sort of wind resistance at all. So, magic physics land, no drag, no frictional forces, all that sort of carry on. And the fact that the only acceleration is due to gravity, which is straight down, hopefully I haven't cut that off, straight down 9.8 metres per second squared towards the centre of the Earth, yada yada yada. So that if there was no drag, then no forces in the horizontal direction, so therefore constant speed, constant horizontal component of velocity. Now what we're looking at is the real world scenario where this stuff actually exists. So we might as well sort of try and get our heads around it a little bit. Now, if you think about any sort of object, any sort of projectile path that you've seen in the real world, you'll notice that they tend to do that sort of thing. It probably needs to be a little bit, hang on, oh wow, that's horrible. Let's see if I can clean it up a little bit. The projectile path of hitting a golf ball or hitting a that's pretty much just as bad, but I hope you get the point. It has this sort of, gradual, and then the tail, I guess, seems to be reasonably steep in comparison to here. So what happens is that those frictional forces actually impact on the velocity components of the projectile, so that the horizontal part, which is that way in this case, and the vertical part, which is up and down in this case, so up at the start, down at the end, are reduced because of this wind drag. Now, there's a few things that we can look at that actually impact on the wind drag itself. Keep looking down because that's where my colours are. One is the coefficient of drag of the object. So the coefficient of drag is to do with its shape. So if you have something that's shaped like this, obviously air trying to rush past this box-like shape is going to have a fairly hard time, and it's going to impact on the size of the force that this shape experiences. If we were to have something that was more teardropped like this, now we're looking at something that's far more streamlined, far more aerodynamic is generally the phrase, which means it has a lower coefficient of drag. So this one here would be high, this one here would be low. So if you look at a truck, for instance, it's got a flat front, really high coefficient of drag, but they're designed like that for a reason. Low coefficient of drag, race cars, things like that, normal sedans, family cars around these days are designed with this kind of shape in mind. They have to put a motor in and stuff, but anyway. Another thing that might impact on it is the frontal surface area, the cross-sectional surface area. So if you look at this shape here and this shape here, the cross-sectional surface area of my teardrop compared to the box, not a heap different. So if you have something that's larger, so the shape will be taken care of by the coefficient of drag. The frontal surface area, something that's bigger, obviously it's going to be caught in the wind more, it's going to have more wind particles applying like little forces against it and things like that, so it's going to find it a lot more difficult to get through the air. So if we have large, that's going to be the high, and small is going to be low. So if we have a large surface area, frontal surface area, we can have a high drag force. If we have a small, so smaller object, low drag force. Other things that impact it is the density of the fluid or the air that we're actually travelling through. So if we have high density, so we've got a high pressure, high density is going to be lots of air particles inside a specific unit of volume, which means that there's more air particles to interact with the particles on the surface of the object, so it's actually going to slow it down more. So high air density is going to impact on the object, no matter what it is, more than low density. The other thing that we're looking at is the speed. So if something's moving faster, it's going to have more wind drag. If something moving slower, it's going to have less wind drag. But it's not actually a linear relationship, it's a squared law. So if we have something where we double the coefficient of drag, we'll get 2 times the drag force out of it. If we have something where we double the cross-sectional area, the frontal surface area, we're going to have something that's twice as big. So if we make the shape go from this to this, we'll make it less. If we make it go from this, half the coefficient of drag, we'll have half the force. If we have double the density, we will end up with double the force. If we have double the speed, though, we're going to end up with 4 times the force. So we're having to square the doubling as well. Alright, so basically what that means is that the drag force is directly proportional to the coefficient of drag, it's directly proportional to the cross-sectional frontal surface area, directly proportional to the density of the fluid or the gas or the liquid, and it's also proportional to the square of the speed that we're trying to push through. So now we can have the force of drag is equal to half I should have put these in order, half AC d rho v squared. Okay, so now we got any object that you can think of experiences a drag force based on these properties. Nothing to do with its mass. Okay, I'm going to get to that in a sec when we talk about terminal velocity. So terminal velocity is the maximum speed. So terminal meaning the end speed, the maximum speed an object can get to. So it will speed up and speed up and speed up. Think of a skydiver jumping out of a plane. They're not instantly at terminal velocity as soon as they jump out. They speed up under the influence of gravity and their own wind drag. So as they're falling downwards, they've got gravity acting against them. Gravity pulling them downwards. However, as they're getting faster and faster and faster, what was a smallish wind drag force, so gravity's still downwards, gets bigger and bigger and bigger. And the difference between these two sizes is the net, is the net force or the net acceleration they're experiencing. So here, a fair bit of acceleration. Here, yeah, a fair bit of acceleration, a little bit less though. And here, we've got the point where our drag force, the white one, the drag force, is equal and opposite to the pink one, the acceleration due to gravity. So now what we've done is reached a point where this thing is equal to something's acceleration due to gravity. So here's our, half CD rho v squared is equal to ma. All right, so now we've got this thing where force balances force. So if two forces balance out, we have effectively no forces, so no acceleration in that direction. Now, on the way up during this this version of events over here, I'm going to redraw that because I don't like that whatsoever. It's still not great, but yeah, we're going to deal with it. On the way up, we have gravitational force downwards. Always a gravitational force downwards. Always a gravitational force downwards. Gravitational force downwards. That's gravitational acceleration, I should say. But on the way up, we've actually got a wind drag force pushing down as well. So we have lots of wind drag. It's not going up as fast here, so we got a little bit of wind drag, but not much. Here we're actually going downwards, so the wind drag force is now upwards. Here we're coming down pretty quickly, so we've actually got a reasonably sizable upwards force. So if we look at the sizes of the accelerations here, both of these are acting in the same direction. Both of these are acting in the same direction. These are opposite, these are opposite. So here we've got lots of acceleration downwards, so it's going to slow it down a lot on its way up. Slow it down a lot on its way up. So this means it's actually going to reach the top quicker than if there was no wind drag at all. So it's going to reach its maximum height sooner. Its time to the top here is actually shorter because its vertical velocity is actually getting less and less and less on the way up, faster because we've got two forces acting on it. We've got the gravitational one downwards, but we've also got wind drag going downwards. Then on the other half of the flight where it's on its way down, it's actually slower coming down than it was going up because we've got gravity pulling down, but we've got the frictional force now pushing up against it. So it's not under the influence of gravity anymore, it's under the influence of something a little bit less than gravity, whereas it was under the influence of something a little bit more than gravity. That means it's not going to have as large a component vertically, it's not going to reach the maximum height that it was going to. That means that its time of flight is a little bit less. If its time of flight is less, flip back to the other video, we need time of flight for the range, so that's going to be less, but also the horizontal component here, that's not a case anymore. we don't have this case where we have no horizontal forces, which means that we do have them, which means that the horizontal component is going to be smaller as well. So because of drag forces, based on this thing here, we have less horizontal velocity, we have less vertical velocity, we have less maximum height, we have less time of flight, so therefore we're going to get less range. Okay.